We will start our discussion on dynamic programming. So the setting is the same as before. It's the same problem, just a different way to solve it. So I have xt plus 1 equals to ft xt ut. I have the performance index minimize j, which now is a function of pi. So minimize over all policy, which is ct plus 1 xt plus 1 plus summation t equals 0 to t ct xt ut, and pi is a collection of policy pi 0 all the way to pi t, and each pi t maps xt to ut. So xt is the state, the set of all states at time t, ut is the set of all actions at time t. In this particular class, we are of course talking about continuous states, but the theory remains the same even if you were in a discrete state setting, discrete state, discrete action setting. Right? So what we had discussed in the previous class, so when we looked at the case where we are just optimizing the action, we are not optimizing the policies, the problem was that it was prone to environmental perturbations. So whatever perturbations are there in the environment, if it perturbs the state, if there is disturbance, then the policy is no longer the sequence of actions that you have computed is no longer optimal for the rest of the horizon. So to counter that, people in the US, specifically Bellman, wanted to solve this problem, and instead of solving it using an open loop control, which is just u0 star all the way to ut star, instead of trying to compute that, he wanted to compute a policy which maps the state to action. And the policy, we want to find the best policy which minimizes this particular cost function. So the problem remains the same, the perspective is different. So now the perspective is I want to optimize the policy. And Bellman's principle of optimality said that this pi star is optimal, this whole sequence of policies is optimal if pi t star is optimal for the truncated cost, pi t minus 1 star, pi t star is optimized for the truncated cost, and so on and so forth, which is what we discussed in the previous class. Now, because of the Bellman's principle of optimality, there is a rigorous proof for it. We are not covering that proof in the class, but there is a rigorous proof that you can read in any dynamic optimization book. Those proofs are somewhat involved, so that's why we are not covering it in the class. So, but what it gives us is a way to solve this optimization problem and find the optimal policy. And so we introduced that algorithm in the previous class for the terminal time step. So how do I find pi t star? So pi t star is supposed to be the argmin of pi t of the truncated cost And so how do I solve this particular problem? Well, I define my Vt of xt is equal to the minimum. Sorry, let me do it with Vt plus 1. So I'm going to define my terminal value function. This is known as the value function. Will be Ct plus 1. This is known as the terminal value function. So the terminal value function is the same as the terminal cost. Now the value function at time t is minimum over ut in, let me just write it as capital UT, Ct xtut plus vt plus 1 ft xtut. And then pi t star of xt is equal to the argmin of the same thing. Okay, so this is where we had stopped in the previous lecture. We said that at the final time, I need to optimize the cost moving forward. So this is the cost to go at time t. I'm going to figure out for every xt, I'm going to figure out what the best action is for that particular xt. So I'm going to minimize this particular cost function. Vt plus 1 is a function of xt plus 1, but I also know that xt plus 1 is a function of xt and ut. So I did that substitution here from xt plus 1 to ft of xt ut. And now my function is purely a function of xt and ut. I'm minimizing with respect to ut. So this is a function of xt. The value function is a function purely of the state. It doesn't contain action at all. It's just a function of the state. Okay. So I'm going to store the minimum value in the value function, and the argmin, which is what the action is, the optimal action, that will be stored in the pi t star, which is the policy. So this is the policy at time t, optimal policy at time t. Okay, so we talked about the rule book in the previous class. So for every xt, you will create this infinitely long rule book by solving this optimization problem. How do you solve this optimization problem? Well, we know a lot of different algorithms to solve this. So for a given xt, this cost is a function purely of ut, and so you can use any of the methods we have talked about so far in order to compute the optimal optimal action. So you can use gradient descent. You can use, in case ut is unconstrained, you can use Lagrangian method if ut contains some sort of constraints. So anyways, there are many ways to solve this particular problem. So for every xt, you will solve this problem, which requires infinite number of iterations, and then there are infinite number of xt's that you need to solve this problem for. So you will have an outer loop of state and an inner loop, which is an optimization solver. It sounds very complicated, so we'll try to simplify it in the subsequent lectures. But right now, let's keep the complication. So the complication thing is, we have infinite number of states, we have infinite number of iterations to solve this problem, but we are willing to take that effort and solve this problem infinite number of times. That's okay. Now, the Bellman principle of optimality said that pi t minus 1 star pi t star is optimal for ct minus 1 plus ct plus ct plus 1. Right? This is the cost to go at time t minus 1. And this is the optimal policy. Like, in order to compute the optimal policy, I have to look at the cost all the way till the end of the horizon, and then I need to optimize. What is the optimal cost? What is the optimal cost under the policy pi t star? So what is ct plus ct plus 1? So this policy is something that I've already computed here. My question is, under that policy, what exactly is the sum of these two costs? So this one is computed. What is this equal to? When I use pi t star as my policy, that's exactly equal to Vt, right? So Vt is the minimum, pi t star is the argument. So Vt is the minimum, so this is actually Vt of xt if I were to use pi t star at the terminal time step. So now I only need to optimize pi t minus 1 star, and we have Vt minus 1 of xt minus 1 equals to the minimum over ut minus 1 in ut minus 1 ct minus 1 xt minus 1 plus vt of xt, and this xt is ft minus 1 xt minus 1 ut minus 1. Okay, so what did we do here? I had already computed pi t star, I had already computed Vt, which is the minimum cost to go at time t. Now I have to compute pi t minus 1 star. I know that pi t star is something that I've already computed, and I also know that under pi t star, the total cost is going to be Vt of xt, because that's something I've already computed. So now I'm going to do the same thing. I'm going to have Vt plus Vt of xt, but I know that xt is a function of xt minus 1 and ut minus 1, so I'll substitute it here. Oh, this should be a function of ut minus 1, right? So this is a function of ut minus 1. So I have the sum of these two functions that are functions of ut minus 1. So at every xt minus 1, I'll compute this optimal solution. I'll store the optimal value as the value function and the argument as a policy at xt minus 1. So remember, we had this infinite number of optimization problems to be solved here for infinite number of states. I have to do the same thing all over again here, right? In contrast, if you remember from the Pontryagin's principle, the backpropagation algorithm, you just have to run that algorithm once infinite number of times. That's it. Now, at every time step, you're running infinite number of optimization iterations. So the two algorithms are completely different. The same problem, completely different algorithm. The second point I want to emphasize, or rather, I want you to discover, is there a pattern here? What is the pattern that you see on the board? A wise mentor once told me that in order to find a pattern, you just need two things, right? So you have the thing at time t, and you have the expression at time t minus 1, and that's enough to find a pattern. So what's the pattern? What are we doing at every point of time? So in order to solve the problem at every time t, or at every time, uh, I have the optimization of cost at that time plus the future value, the value at the next time step. And the same thing happens for pi t minus 1 star as well. So that's the dynamic programming algorithm. So Vt of xt equals to minimum ut So this one is run again in a backward fashion. So you solve the problem at capital T and then you go backward from there. Right? Yes.
Is this algorithm only optimizing over the optimal, like definite trajectory? Like the states are definite. You don't have different states at the same time.
What do you mean by different states at the same time?
Like if you go forward, you can have a lot of states.
Correct.
You can
Correct.
vary.
That's right.
Then
That's
go
right.
to the next step.
That's right. So you are doing this, you're solving this problem over the entire state space at every point of time. So all the possibilities are covered.
Oh,
So at time t, you're looking at all the potential possibilities of the state, and then you're solving this problem. At time t minus 1, you're looking at all possibilities of the state and you're solving the problem.
but once the time step is solved, that state is fixed. Or
The states are not fixed. So let's say you have solved this problem all the way up to time 0. Now what you have is pi 0 star, pi 1 star, pi t star, right? So remember that solution is backward, but time actually moves forward. So at time t equals to 0, you look at the current state, you look at this lookup table, you figure out, okay, pi naught star of x naught star, oh sorry, x naught, not x naught star. So pi naught star of x naught is this, so I'm going to do that action. I'm going to execute that action. And then the state will transition to x1. At x1, you will look at this particular lookup table, pi 1 star of x1, and then you will execute that particular action. And then you will keep continuing that all the way up to the end of the horizon. So you compute this in a backward fashion, you execute it in the forward fashion. Okay, and I'll do an example on the board right after this. So you will see how exactly to apply this in practice. Any other question? Okay. All right. So at the end of the computation process, so you ran infinite number of optimization problems at every point of time. You've created this infinitely long rule book at every point of time, all the way up to time 0. Now you have the sequence of policies at every point of time. And you can think of each of these sequence of policies as a rule book, as a handbook. And every time you are at a state xt, you look at the corresponding handbook at time t, and you figure out, okay, this is the action that I was supposed to take, so let's execute that action. Okay, so in this case, remember, this is the policy that maps the state to action, where we are trying to optimize an optimization problem. How many of you have taken 3551? A few people. So remember, in 3551, we talk about design of PID controllers, lead lag compensators, and so on. So you can think of those PID controllers and lead lag compensators as policies, but those policies are not optimizing anything. They are optimizing the rise time, and not optimizing, but they are meeting the rise time requirements and settling time requirements and the steady state error requirements and so on and so forth. So they were just requirement. Then there's no optimization there. You're not trying to optimize something. You're just making sure that there is some baseline performance that you need to meet, and you're designing policies using PID controller. So this pi1 would look like a PID controller, and the policy is not changing over time. Once you design a PID controller, you put that on the system and then you forget about it for the rest of your life. So the PID, so I have a 20-year-old car. The PID controllers 20 years ago was put on that car. Even today, that same PID controller is running that car. It hasn't been changed since then. Right? But here I'm talking about optimization. I have a specific cost function I'm trying to optimize. So these policies are actually created to optimize that particular cost function. So in some sense, these policies are changing with time because there is the end of the horizon effect. And so there is no like sort of invariant policy, time invariant policy, a policy that doesn't depend on time. So that way you cannot, you have to keep solving this optimization problem at every time you are exposed to a new optimization problem, you have to solve this entire problem all over again in order to get the sequence of policies. So if you think about it from an autonomous car perspective, of course there are, within a car there are engine, there is batteries, there are like whole bunch of things, and you generally tend to use PID controllers in these low level tasks. But at a higher level task where you have to figure out how to do the path planning in order to get to the destination. So on every day your destinations are going to change. Sometimes you're going to Kroger, sometimes you're going to Giant Eagle, sometimes you're going to do shopping, or sometimes you're just going home, right? So depending on the destination, the autonomous vehicle is trying to solve this optimization problem. The cost function could be either fuel, the cost function could be traffic, the cost function could be total time, like you want to minimize the total time to get to your destination. So depending on your cost function, you will come up, the autonomous car will come up with a set of policies, and then it will execute that policy as the new states are encountered. Any questions so far? Okay, so I hope this clarifies how it connects to the feedback controls class that you might have taken during an undergrad. So in feedback controls class, you were designing this using Bodhi plot, Nyquist plot, and whatnot. And you weren't really optimizing anything. You were just trying to meet some performance specification. Now we are trying to optimize the cost. And instead of doing low level control, now we are doing some higher level decision making task. Okay, so this cost function will change every time you are on a new mission, right? So these cost functions will change, and accordingly you will have to come up with different policies to optimize the specific cost function. Okay, wonderful. Uh, if there are no further questions, are you all convinced that in this particular, this is the output of this dynamic programming algorithm? And so if you look at any truncated policies, set of policies, it's optimized for the truncated cost function, okay, by virtue of this minimization approach. And the second thing to remember is that you compute these optimal policies backward. So you have to start from the terminal time step, and then you have to come all the way to the initial time step. So one of the assignment questions for you in assignment 6 is what are the differences between the optimal policy that you get from Pontryagin minimum principle and what you get from the dynamic programming. So one obvious difference is that you get a closed loop policy. So now your action is a function of state, whereas in the PMP, the action was not a function of state. So you had U0 star, U1 star, U2 star, all the way to UT star. So it was no longer a function of state. Here it's a function of state. As a result of which, the optimal policy you get there is so let me so it's not, as we had discussed in the previous class, the optimal policies there is not robust to the perturbations in the environment. So perturbation could be somebody walking on the road, or air at gusts of wind in the environment, because of which your state might change. So the Pontryagin maximum principle based approach doesn't give you optimal actions that are robust to these perturbations. Whereas this one, suppose a gust of air came and then your state has changed, you still have the policy, optimal policy, and therefore you can execute that optimal policy moving forward. Okay. So let's look at an example. I'm going to do an example. We'll solve the example both using the PMP and the and this dynamic programming algorithm, and then we'll try and see what kind of results we get. This is again part of your homework, so it'll help you solve the problem in your homework easily. So here is the problem. So this is known as a resource allocation problem, dynamic resource allocation problem. I'll let you guys write and then we'll talk about it. Okay, so here is the setting. I have, this is all in R by the way. So xt is in R, x0 is strictly greater than 0, and ut is in R as well. In fact, ut will have to be positive because we are taking the log here, and xt always has to be positive because we are taking the log here. So it will turn out that the optimal solutions will always be positive, and ut has to be between 0 and xt. Let me write it as ut. Yeah, this is fine. Okay. So this is the problem setting. So here is the idea. I'm going to retire. X naught is the total amount of money I have in my bank account. I'm going to live for the next 30 years or 40 years, whatever. So I have to come up with the capital T, 40. At every year, I have to take out a certain amount of money from my retirement account. So I'll be left with this much money in my retirement account in the future. What is the enjoyment? Sorry, this is the cost, right? So I have to put a negative sign. Can you please add a negative sign to the cost function? So if I spend $1, I'll get some reward. If I spend $100, I'll get some other reward. If I spend $1,000, I'll get some other reward. So suppose you don't have any money, you have zero money, you get the first dollar, what are you going to spend it on? Food, most likely, right? You get a reward of log of 1. Now you have $100, what are you going to spend it on? Most likely better food, okay? So you have log of 100 is your total reward. If you have $1,000, what are you going to spend on? Maybe better food and a better home for yourself. So that's log 1000 is the reward that you are getting. And so as you keep increasing the dollar amount, the amount of marginal reward that you are getting is much smaller. Okay. So every time you get, if you are at $100,000 level, you get one additional dollar to spend, it's not going to make a big dent in your life. So that additional $1, it was extremely important when you had $0. That additional $1 meant a lot to you. But at $100,000, that additional $1 means nothing to you. So the way you capture that phenomena is by taking a logarithmic reward function. Log of ut is your reward. So because we are doing a cost minimization here, so I'm going to add a negative sign because negative of reward is cost. So I have, and then this is the amount of money that you will leave to your heirs, xt plus 1. So at the end of 40 years, you're dead, and then xt plus 1 is the amount of money left to your kids. And the reward that you are going to enjoy after you are dead is log of xt plus 1. Okay. This is also true in the case of, I mean, there are many variations of this problem. This is the simplest problem, so we are trying to solve it here. Another variation is you have an interest that you are earning from your retirement account. So you multiply xt by 1 plus r, which is r is the interest rate. So that way your wealth is growing at every year, and then you're withdrawing some amount of money from that particular wealth. One other case where this particular theory is applied is resource extraction. So you have lithium mine. X naught is the total amount of lithium in the mine, and you have to figure out every year how much lithium you want to extract, and then the cost there is the revenue that you're going to earn. I mean, negative of revenue that you're going to earn from that lithium every year. So hopefully lithium prices are going to go high in the future, so you want to extract as little lithium as possible in today's year, because you want to wait for 2 more years when the prices of lithium will go high, and therefore you will be extracting a lot more lithium at that point of time. So mineral extraction, oil extraction, retirement accounts, savings, and so on, you kind of use this sort of framework to solve problems of those types. Now in lithium mine, there is no interest rate. Okay, so in lithium, there's no interest that the nature gives you, because you're storing lithium underground. So whatever lithium is there, it will remain there, and after t number of years, you will no longer have any lithium underground. Okay, so okay, so that's the setting. Let's solve it. Uh, let's solve it using dynamic programming first. Let me assume that t equals to 1. So I'm trying to minimize over either pi or u c2 of x2. I'm just trying to solve the simplest problem. So either I'm going to minimize over pi if I'm using dynamic programming, or u if I'm using Pontryagin minimum principles. Sorry, Pontryagin maximum principle or minimum principle. It doesn't matter. I'll call it P and P. So this is the problem. So this is minus log x2 minus log u1 minus log u0. Okay. Which one should I use first? Let's use dynamic programming first. So I want to recall a result from something that you will prove in your assignment. So I don't want to prove it in the class. But if you are minimizing u in 0x minus log u minus a log x, then argmin u star is x over 1 plus a, and the minimum value is minus or ka minus 1 plus a log x. Oh, sorry, not log x minus u. So Ka is a constant. This Ka, it's a constant. Let me write what Ka looks like. A log a minus a plus 1 log a plus 1. You know, I think there should be a negative sign here. Yeah. So this is a result that you will be proving in the assignment. So this is part of assignment 6. And it's not too difficult to prove. So this is a convex function of u in the interval 0 to x. You will prove that, and then you will take the first derivative, set it equal to 0, you get this. You substitute u star in this particular expression, and you get this expression where you have a constant that depends on a. But remember, constants don't participate in optimization, right? So we can ignore the constant. This is the only thing that is the important term in the optimization. So let's go back to this expression. So what is my v2 of x2? I need your help. What's my v2 of x2? Can you check back into your notes? What's the terminal value?
Is it like C2 and X2?
Yeah, C2 of x2. So that's minus log of x2. That's right. Minus log of x2. What about v1 of x1? This is minimum of u1 in 0 x1 minus log u1 minus log x1 minus u1. So what is this v1 is going to look like? It's k1 minus 2 log x1. Right? I've just used this particular result. What about pi 1 star of x1? That is x1 over 2. The a here is equal to 1, so I have x over 2. So I get x1 over 2 term. Remember, I was telling you that you need to have infinitely long rule book in order to be able to say what you should do at every state in pi 1 star. So in this case, the rule book is not too long. Okay, it's very easy to execute a function or store a function in the memory which says 1 over 2 of x1, 1 over 2 multiplied by x1. Okay, so there are some cases where the policies can be written down fairly easily. What about v0 of x0? That's minimum of u0 in 0 x0 minus log u0 minus 2 log x0 minus u0 minus plus k1. Does k1 participate in this optimization? It does not, because it's a constant, so constants don't participate. What is the solution here? This would be k1 plus k2 minus 3 log x0 and pi 0 star x0 is x0 over 3. I'm just using this result, these two results. So this is an optimization problem that I can solve by hand, so that's why I'm covering it in the class. Very easy and simple. Okay, so I've solved this problem. So let's say I have $300 at the beginning. So x0 equals to $300. That's what I have at the beginning of my retirement account. How much money should I spend in year 1? 300 over 3, $100. What's my x1 now? $200. Okay, so x1 is $200 because I had $300. I spent $100. I have $200. How much money should I spend in year one? $200 over $200. And then this is what is left at the third time step, V2 of X2. Okay, so it seems to me that the optimal solution is saying that you spend equal amount of money at every year, and at the end of the horizon, you will be left with the same amount of money. So $100, $100, you're left with $100. That's the optimal solution in dynamic programming. But you know what is the funny thing here? Let's say somebody gave you an additional $10 in year one. So you did some nice work for the church or charity or whatever, and you got a gift card, Amazon gift card of $100. So sorry, of $10. Now, how much money should you spend in year one? Now you have $110 here, right? So you can now spend, sorry, $210 divided by 2. So now you can spend $105 in year one. So even if there was a perturbation in the original state because of some good thing that happened to you, you can update your action because what you have done is computed the closed loop policies, which takes into account the current state of the system to figure out what the action should be. Alternatively, let's say you got hurt and you had to buy bandages worth $10. Okay, in year one. So in this particular year, so now you're only left with $190, and then you can adjust your expenses accordingly. So you only spend $95, and then that's optimal for the rest of the horizon. So now you understand why closed loop policies are better, right? So you can adjust your actions according to the current situation. Okay, wonderful. So I have done the closed loop thing. I want to write down the solution somewhere, so I'll write it here. So pi 0 star x naught equals to x naught over 3, pi 1 star x1 equals to x1 over 2, and the value function v0 of x0, what is it, minus 3 log x0 plus some constant v1 x1 equals to minus 2 log x0, sorry, minus 2 log x1 plus constant, and v0 x0 equals to minus log, sorry, v2 x2 minus log x2. Okay. Let's do the let's try to solve it using the PMP. So what was the result? U0, U1 star is optimal, imply there exists P1 star, P2 star, sorry, P0 star, P1 star and P2 star such that UT star gradient U of HT equals to 0. Right, so let's write down what the Hamiltonian here looks like. So what is my H of T? XT UT PT plus 1. I think it is PT plus 1 transpose FT XT UT. Can you please check if this is indeed the case? Is this what the Hamiltonian is? right? Is that the Hamiltonian? Okay. So wonderful. So what is my H1 of x1 u1 p2? That is p2 times x1 minus u1 plus minus log u1. Does that make sense? Does that look correct? What about h naught x naught u naught p1? Okay. So what's the gradient of h1 with respect to u? What is the gradient of this with respect to u?
minus grade into p2 x minus 1 x naught minus u1.
So minus p2 minus 1 over u1. So gradient of log is 1 over the number, and x1 is not dependent on u1, so you have minus p2 times u1 here, so you get minus p2. Same thing here, u0 okay. Now I need to find out the co-state vectors. So how do we find co-state vectors? Backward. Okay, so we start with p2 and then we go all the way to p1. So p2 equals to gradient of x2 of c2 at x2 star. So p2 is what is gradient of x2? It's minus 1 over x2 star, which is minus 1 over x0 minus u0 star minus u1 star. P1 equals to gradient of x2 x1 of h1, which is p2 which is the same as minus 1 over x0 minus u0 star minus u1 star. So this is evaluated at star. So P2 star is minus 1 over x2 star. P1 star appears to be the gradient of I think P0 is something we don't need. We don't care about the co-state vector at time 0. It doesn't appear anywhere in the expression. So what is my U1 star? U1 star equals to minus 1 over P2. U0 star equals to minus 1 over P1, which is minus 1 over P2, P2 star. So the co-state vector along the optimal trajectory And so u1 star is the same as u0 star. So I get u1 star equals to u0 star, which is equal to what is minus 1 over p2 star? Minus 1 over p2 star. This is equal to x0 minus u0 star minus u1 star. Does it make sense? Any questions? So what's the approach to solve this problem using the PMP? So I write down the Hamiltonian for every point of time. I take the derivative with respect to u. I take the derivative with respect to x. The derivatives with respect to x gives me the co-state vectors. I substitute the co-state vectors here in order to get the u star in terms of the co-state vector. And then in this particular problem, I was kind of able to eliminate all the co-state vectors, and I got u1 star has to be equal to u0 star, and u0 star should be equal to x naught minus u0 star minus u1 star. So what does that give you? What I get is I think I'm missing something. What am I missing? I'm not able to compute. Am I missing something? I'm able to compute u1 star. I'm able to compute u0 star. I'm able to compute this. I think there's something about x2 star that I'm missing. What I should get is, what I'm trying to get it is u0 star equals to x naught over 3, u1 star equals to x naught over 3, and x2 star is going to be x naught over 3. So that's what I want to get to, but I think I'm missing one particular expression. I'm not sure what that is.
But also, you wrote that P2 star is equal to minus 1 over x2 star, so you can use that.
Oh, yeah, that's right. Very good. This is equal to x2 star. Yeah, perfect. That's exactly what I was missing. So u1 star is equal to u0 star is equal to x2 star, which is equal to this. Perfect. So now I get x2 star equals to x naught over 3, u0 star equals to x naught over 3, and u1 star equals to x naught over 3. So what did I get here? I got the optimal solution purely a function of x naught, okay, of the initial state. What happens if you have to buy bandages for $10, or what happens if you get an additional $10 Amazon gift card in the middle of the decision process? There's nothing that you can do in this approach to be able to account for those perturbations that have happened. Okay, so I think we are out of time. It's 1:34. We have just 1 minute left into the class. But there are a few things we did. We understood how to apply dynamic programming to solve the problem. We understood how to apply PMP to solve the problem. We identified properties of the policies that I get out of dynamic programming and properties of the optimal solution we get out of the PMP. In the next class, I'm going to start from here, and I'm going to show you some more properties of the kind of solution we are getting, and that will be on Monday. Today is Wednesday, right? So we'll meet on Friday. Okay. And next Wednesday, you have your midterm too. All right. Thank you.